Hello everybody. So as Stephen said, my name is Bayle. I'm a final year PhD student at the University of Bath in the UK. And today I'm going to talk to you about the Dynarel experiment, which was conducted in August and September 2017, almost 2 years ago. And the experiment, the global aim of the experiment was to test a prototype structure called the dynamic cobalt burn revetment in Jibril. So, have a new toilet.
May I just?
The session is under.
It's
there's a problem. Right there at the back. Sorry about that. That one.
So once again, hold there.
Alright, here we go. So yeah, I'd like to thank all the collaborators in this experiment, so with my university, my funding organisms, the hosting institute, FFA, and all the staff and people involved, technicians and everybody was really great work with them. Hydrolab obviously, and then all the institutes, research centers and universities involved in this quite international project. So yeah, that's definitely. So we have 3 objectives in this project, which are going to structure my talk today. So as I said, we aim to test a type of structure, a coastal protection structure, the dynamic cobalt burn revetment. So I'm going to quickly explain what is the dynamic cobalt burn revetment, what is the idea behind this experiment from the start. So, the concept of our protection is based on natural composite beach. And so here you have an example of a natural composite beach in Bayle, in Wales, in UK. And so basically a composite beach is composed of 2 different types of sediment, usually sand and then a type of gravel. And then the key part is that the sediments are actually distinct from each other, except at the toe of the reef, where they're a little bit mixed. Usually they're well and so at low tide, you usually have the sand part of the beach which is exposed, so the shoreline is far away from the gravel reach, and then at the time the tide comes up, you have the water getting closer to the beach, and then eventually to the gravel. So during storm surge, during energetic events, this gravel reach is a highly energetic and dynamic feature, with both short segment transport, long short segment transport, a lot of things happening. It has been recognized as a natural protection for the hinterland because it breaks the wave energy and reduces the wave running. So we based our concept on that, and because we wanted to work with we wanted to use the work with nature approach, we basically tried to mimic, replicate the behavior of a composite beach by installing a gravel berm with a certain design at a certain location of the beach. Because a given sandy beach can given wave condition. So how does it work? Basically, as the waves interact with the structure, they interact with the cobalt, they push them landward to what we call groundwater transport. So as the water level increases, for example, in the storm surge, the groundwater transport is intensified because the interaction between waves and cobalt is bigger, and so the pebbles finally end up in the location. The structure is supposed to move upward and downward at the end of the time. So theoretically, this structure is supposed to dissipate wave energy and protect the hinterland against wave attack, while keeping its global shape and then reducing wave runoff, but also while self-maintaining a relative elevation to sea level. So that's the theory. We go back later on the actual design of the revetment in our experiment, but this is just for you to understand what we tried to achieve. So here comes the second objective, which is to test this structure in the laboratory Flume. So as I said, we run the experiment in G3UK Flume in Hanover. So you probably know that Flume is just a photo and dimension, just to say that we had the opportunity to try test the structure at full test. Obviously, we use the in situ instrument and the profiler with gauges and so on. We also install 3 overhead LiDAR on the roof of the Flume. And then we install to cover a wide range and then to overlap as well. And basically, we're measuring the free space elevation in the entire Flume at a frequency of 25 Hz. So you have an example here on this video of type of data you get with it. So you've got 3 colors, 3 different LiDARs, and they give you basically the free space elevation and the flash area as well. You can get runners, you can get wafers, and we also wanted to track some bubbles within the revetment. So for that, we use the technical RFID. So basically we drilled into 97 pedals. We installed a passive integrated transporters, and then basically each transporter got a unique ID, so you can detect them with the antenna, and it tells you where the transporter is and which bubble it is. So if you know where you place it at the beginning, and if you find it at the end, you know how much. So I just presented those 2 instruments because that's the one which are important for this presentation, but we also have a wide range of instruments for you to do to measure hydrogen and get it. Okay, so that was for the facility and the instruments. I'm going to quickly present the procedure because I'd like you to understand what we try to achieve. So basically, the objective was to get 2 comparable data sets. So one just with the standard beach, and then one with the standard beach with the protection. So we were running the same wave condition, then we can compare the 2 data sets and access performance of the protection. So because of that, we split the experiment into 2 phases. First phase is for SD, for standard beach. So we started with a planar beach profile with a slope of 1 over 2. For the rest of the talk, just quickly on the coordinate system. So X increases towards the beach, 0 is at the wave paddle, and then Z, 0 is at the bottom of the beach, increases upward. We define our standard wave condition to be quite erosive, and then starting with the 4.5 meter water level, we run 20 hours of these waves to get like a developed beach profile, and then we raise the water level using 4 steps of 10 centimeters. And finally, we run what we call a resonance test, which basically is a set of image waves, like storm waves and accretional resonance. That's for the first phase. The second phase, phase VR, started by manually reshaping the beach to initial planar beach profile, with the 115 again. And using the same wave, still without the revetment, we ran 20 hours of wave to get a normal development. At this point, then we constructed the wave. So here's a photo of the revetment in the Flume. So we chose to have a steep cone slope in physical agreement with the side of our couple, and then we set the flow of the revetment at 4.8 meters elevation, and the crest was 60 meters higher than the floor. So then ended up with this type of length, and we ended up using the lines. And then, because we want 2 comparable data sets, we did exactly the same thing using the same wave condition. So 4 steps of to the right, let's say, water on the right, and then a resonance test at the end. So as you can see, we have 2 comparable data sets. Same wave condition, same order of energy. One without the structure and one with the structure. Okay, so let's have a look at the behavior of the revetment in the. So here you got the structure just after its construction. And the structure after the first level, the first water level, second water level, third water level, 7 hours breathing the 4th water level, and then at the end of the 4th water level. I'm just going to stop here for a minute. So basically, on these plots, only the water level change, okay, the same way from the gray area is the revetment, it's not concrete, bubble, remind you. And then the green area is what I call a single layer of bubble, basically a mix of sand and bubble, which remains there as the revetment tree. So they kind of left behind a revetment landscape. So I would like to draw your attention on the fact that the sand at the sand underneath the revetment is actually getting eroded. Because when the waves come, the water percolates to the structure, and then the sand is getting eroded. As you can see, the flow is actually decreasing, flow elevation. But this is not a good thing because it makes the revetment steep a little bit. That's not something we want. It also dims the revetment with the slope getting steeper. But yeah, the revetment will steep. But the good point is that the sinking process is actually compensated by the flow over transport. We have the pebble going on top of the crest, and so making the crest thicker, and the actual elevation, the absolute elevation of the crest remains stable. Even with the sand being already under the revetment remains stable because of the flow over transport. So let's have a look at what happened when we run airways condition, like storm condition. So you can see because of the more steep wave, this rollover process is intensified. So you have the pebbles are spread landward on the beach, and you see the crest thickness being improved. So again, this is not something really nice because you don't want to end up with all the bubbles spread everywhere on the beach because you would be a layer. The good thing is that after recovery test, it comes back to the previous shape and previous shape quite similar. So you get the crest thickness, which is thicker again, and then because of the roller transport at this stage, the crest elevation is higher than what before. So it self-maintains its own shape and also its elevation. The wind layer gets longer, obviously, and so that's what we call a dynamic study. The revetment is stable in shape, but it's dynamic because it moves and moves. If we have a look at the shortened behavior, so on this plot, we've got the time, and then across on the y-axis we've got the cross shore. So here the land, and here the sea. Red is for erosion, blue for accretion, and the dashed line are each water level change, and the thick dashed line are for erosion condition and for acquisition. So as you can see, you have a lot of changes. So the revetment was good here, and then it keeps changing. You see the elevation change per second. So it's really highly dynamic. This movie is supposed to show you the elevation change, the bed change per minute. Working. It's actually the side view of that one. If we go into detail into this, so on the upper plot, so the time again here, and then on the y-axis you've got the growth change. So the growth change is like how much the revetment moves. Alright, it will represent how much pebbles, how much bubbles moves given the revetment. And then on the bottom one you've got time, and you've got the net change rate. The net change rate is more how the revetment shape differs from its previous shape. Okay? So as you can see, it increases with the water level, and it also increases with overtopping, but then it kind of decreases and stabilizes a little bit. But the good thing, the important point here is that the gross change is on average 10 times bigger than the net change. It means that the revetment is stable. It doesn't change. When it doesn't change that much for its previous shape, it's still moving 10, the cobalt are still moving 10 times more, and that's all change of the revetment. So it means that it's stable, but it's highly dynamic. And this is a table just showing the instrument cobalt transport, the one with RFID system, the one with drilling grid. So it shows mainly landward transport. It explains the roller transport, and also explain why the crest gets higher, and also explain why the revetment is stable. So if I have a look at the performance of the revetment in terms of wave run-up, so here we got time, and then this is the wave, the run-up excursion and the run-up height. Red is no dynamic revetment, and black is dynamic revetment. As you can see, when the dynamic revetment is there, the run-up is reduced, which is a good thing to protect the hinterland, because it reduces the wave attack of any structurally handling the hinterland or any habitat, and also it decreases the shoreline. Okay, so as conclusion, we tested a new protection in laboratory Flume. So despite constant changes, so even if the revetment moves a lot, there is a lot of things happening. The bubbles are always dynamic. It remains stable. The crest itself upgraded to a higher level of protection because of the rover transport. The rover transport has been demonstrated by the transport bubble, the instrument bubble, and the revetment decreased the run-up and the shoreline session as a result. And so on this experiment, we have already 1 paper published, and then 3 ready for submission, and then 2 integrations with one really valuable experiment with the huge data set that we think is better. Just quickly, this is an ongoing collaboration. For the last 6 or 8 months, we've been developing a collaboration with the Department of Technology, the Washington Department of Technology, with George Kaminsky, and the community of Norfolk, because in this area, the community grew kind of a dynamic of Revetments. So I went there in January to get some field data, and so I'm aiming to compare them to the data, so the same behavior and things like that. So it's actually an applied protection, and hopefully it's a nice project for people who can use it in all the places around the world. And that's it for me. Thank you very much.
Yeah, thank you very much, Paul. Any questions? Oh, many questions, not any. Yeah, Ivan.
So the recovery condition are the same condition that the standard was. So we run so standard wave condition for all these tests, and then in the resilience test we had high energy condition. The recovery are again standard wave. So we run the same way than before. Yes. Yeah. Of the bar. Yes. Yep. Yeah. Good. Good. So because you have also a lot of reflection, yeah. Right. I haven't explored one technically. I have looked at the profile and was different from yes. But yeah, it's something you can look at.
Maybe we can allow one more. I don't know. Ladies first, or yeah.
Yeah. Right. Okay. Yeah. I see a point. So it's not just about how it protects and also you bring a new material into the environment. What does it do to your species and everything? Again, not really my field, but it's definitely something that should be considered. Probably on a case by case, like if you want to go down your vision, maybe doing the study, something to consider. But no, I haven't considered that. So I think it's a little bit more